I thought I told you that yesterday.
You did,
Oh,
sort of.
sort of. And I assume that Eli posted things in a timely fashion.
Did I?
I don't know.
Yeah, I did. It went up yesterday afternoon.
Yeah, so anyone who wasn't at the homework session could have viewed the homework session and gotten it.
Which, shouldn't we be able to do the homework before the day before?
Yeah, okay, so here's what I would expect, right? That, so there are 3 stages, let's say, to doing the homework, maybe 4 stages.
5, so it's like grief.
If we include despair and grief, yeah, all right. No, but the idea is that you work it, you know, you go through and you work through it, and then there are some issues that come up. And as they come up, you can ask me, and probably in about half of those cases, I will have done or thought about the problem, and then I can give you a legitimate answer. Otherwise, I'll give you an illegitimate answer. But usually when I don't know, I'll say, well, I haven't done it myself, but I think this, right? So you work everything that you can up to Wednesday, when on the Wednesday before, the day before it's due, I finally thought about it and have usually a cute way of getting through it, or a trick that I'm going to mention to you. But the trick should only apply to a small fraction of the problems, right? So there was, I can't remember who asked the question, whether it was you or not, that had to do with my labeling of K.
What was me?
Yeah. And I think that I posted that maybe one day earlier than Wednesday, as soon as I realized that there was a problem, I think. Did I?
I think that was Wednesday morning.
Okay.
That's how you
Wednesday morning. So as soon as somebody asks me about something and I realize there is a problem, I'll make an announcement. So if you had asked me on Friday, then everyone would have had the weekend with the corrected question. And then the next stage, you know, you've got as much done as you can. There's just a little bit left. Then you come to the Wednesday session and you get that extra little bit that's needed to finish the homework. So I'm viewing as you're just finishing the homework on Wednesday night, not waiting until Wednesday afternoon to get all of the tricks and be led through the problem. Wednesday afternoon is after you've done everything else. That's the way I think of it, at least. Should I move the homework session up a day? I could put it on Tuesday afternoon.
Why not Tuesday afternoon?
Oh, the only time I'm free is 2 to 4.
Class.
That would work for me then. What class do you have?
Foundations of analysis.
Oh, that's just you.
It wasn't so much that it being on Wednesday so much as the full width and half maximum question. How were we supposed to have any clue of how to do it?
Yeah, it's the last little bit of the, if I remember correctly, actually, I think that it might have been Ryan and Evan came up with a cute way that had to do with, I forget what.
Series expanding it.
Series expanding it, yeah. Was Evan, I gave Ryan the credit for that. I think I should. Yeah, I hadn't thought about doing it that way. And that's the other thing that I count on you doing, is that as Wednesday afternoon comes up, each of you have tackled the problem in your own way, and then you talk with each other, and I'm almost unnecessary to the process, because each of you has figured out a cute way, or not cute, has come up with a viable approach. Okay. Or at least one of you has come up with a viable approach. Waves at boundaries. I had the feeling that I drew my wave vectors upside down to my nose last time around. It seems different. Right. That I drew I could only get yellow chalk. So there's my interface.
Why am I thinking of the magic school bus right now?
here are my dielectric impermeability constants, functions, normal to the interface. Let's see. Actually, yeah, that's fine. Incident wave. So this is the wave vector of the incident wave. I have a reflected wave. See if I
Thank
can
you.
get resonant frequency out of the audio. My reflected wave, which I may have changed my labeling from last time, but the idea is the same. K prime, and a transmitted wave. K double prime, K prime. And I have my incident angle, my reflected angle, which I'll label double prime, and my transmitted angle. And I'll warn you that in about 10 minutes, I'm going to make those things complex. And then you can't make a drawing like this. I think I labeled this was the z-axis, this was the xy plane. And we demonstrated last time that all these vectors have to lie in a plane. That plane is called the plane of incidence. Transmitted, reflected. Yep. I think I got everything up here. All right, and then for just one of the waves in one of the regions, the incident wave, I'll just remind you that we represented the incident wave like this. It's amplitude and a direction, and the direction of the vector direction of the electric field could be taken for our purposes of analysis to either be, because remember that the electric field is perpendicular to the wave vector for all of these waves, okay? That the electric field is gonna sort of sit in this plane. If I chose a point there, it's gonna sit in this plane. I can choose two possibilities. I can take the electric field to be perpendicular, and I will call that, sorry, not perpendicular, to lie in the plane, and in keeping with convention, I'm going to call that P polarization. Or it can lie perpendicular to the plane of incidence, which in keeping with convention is called S polarization. And anything that I want to analyze that's happening with respect to this surface can be broken into the response and reflection and transmission for P polarization or for S polarization. Okay? In the plane of incidence or perpendicular to the plane of incidence. So any analyses that I do will have to do with either that or that, and anything else, elliptical, circular, linear polarization that's not one of those, can be created out of those two by offsetting them in phase, for example, just as we did with circular polarization, or by changing their amplitudes. Okay, so I can do a general analysis of what goes on by looking at that. So I'm just going to write this with, and unfortunately that's what they do. I just choose a direction for the electric field, which is perpendicular to the propagation direction. KDI BK dot propagation. Okay, determines the propagation direction, and then that would be the spatial vector minus omega t. And Ohanian may write it like that. all that that is a multiplication by e to the I pi. So that just means it's a phase shift of the whole way. Sometimes there's a minus sign there, sometimes there's not a minus sign there. Yes.
His is actually weirder than that. He's writing the one without the minus sign, but he's writing it with a minus sign and then omega t minus k. So he chooses.
Yeah, I would actually say that may be because he's sort of setting a priority on the time axis, let's say. Let's say, actually I will say that every optics textbook that I've ever worked in has expressed it this way. So I'm going to leave it this way because I'm used to doing optics. Okay, and yeah, because I mean Ohanian uses CGS units. He's already weird.
At least he's not using natural.
Am I hearing questions? Let me.
All I said was at least he's not using natural units.
No, I wasn't you. I was hearing
Oh.
a murmur from elsewhere in the crowd. And that would be my magnetic field.
Mu and epsilon prime or mu and epsilon?
Oh, in whichever material we're propagating in. All right. So for the, oh crap. That, I prefer that. Since this is K prime, let's make it mu prime and epsilon prime here. In which case what I wrote here is correct, but what I wrote here was incorrect. Just took you in the wrong direction. All right, I look at Maxwell's equations and from requiring Maxwell's equations to be true, that is that I can do line integrals around little loops and area integrals of charge enclosed. I come up with now a set of relationships that have to apply to electromagnetic fields and waves at this surface. Oh, actually, do let me say this. I'm talking specifically about a traveling wave, and the relationship between the electric and the magnetic field here are the result of the fact that I'm talking about a traveling wave. I wouldn't have this locked relationship if I could separately create an electric field and a magnetic field through the action of currents and charges. I can have any angle that I like between E and B, but I won't have a propagating traveling wave. All right, so I've already put a set of constraints in here. And when I have that constraint, those constraints, relations between E and B, and Maxwell's equations having to be obeyed in the absence of free charge, then I have this relationship. I don't think I wrote this last time. I'll only write down a few of them. That is the normal components of the electric field, of the D field, have to be continuous. D per 1 equals D per 2. That's all that I'm writing there. No free charge. Okay? I'll write another one for the E field and just allow the H and B field to, I won't write them out, they're in my notes, and I posted the notes. That's this one. E0 plus, E0 double prime. Actually, I should come back and talk a little bit more about this. E0 prime cross n is equal to 0. E1 parallel to the surface, E2 parallel to the surface. So that's what those things are saying there. But you should, for a moment, stop and think about, okay, what does this mean? Is at any instant in time, I'm going to have an electric field right at this surface here. And the incident electric field, let's say for the P field, is going to point right at that instant, off in this direction, like so. All right? Right there. And then inside the material, I'm going to have an electric field, which is going to be pointing this is right at the interface. So at the interface, I have that field from the incident wave. I have this field from the transmitted wave. What did I have it labeled as? Prime. Right? And I have a field from my reflected wave. All right? And the sum of the three fields has, because I have to have the fields continuous as I pass through the surface, the sum of the reflected wave, which is going to be either this way or that way, right? And those, yeah, actually that's not so bad. The double prime, okay? The sum of the reflected wave plus the incident wave at the surface has got to be equal to the transmitted wave. Let's see, if I'm just drawing E fields here, then it's in the plane. That's got to be true. Okay, that's what the cross product is telling us. In the plane, E field's got to be continuous, right? Perpendicular to the plane, D field's got to be continuous, and I just asked, how do I have to put those fields together in order to make that continuity work at the interface, okay? So whenever I write down a continuity equation, I have my incident field and reflected wave on one side of the interface, and my transmitted wave on the other side of the interface. And at the interface, those have gone in that way. Yes, right.
Why do you have the reflected wave going both directions?
Oh, I'm saying, I don't know what direction the electric field is pointing there. We need to work that out. It could be in phase, or it could be 180 degrees out of phase with the incident wave. All right. In fact, when I go from a low index of refraction to a high index of refraction, I do get a change of phase. And that's easiest to see if I think about low index of refraction. I got a big field. Let's talk about the S field, all right? The S field is looking like this in the surface, all right, for that surface. So I'll just point, it's about that big, all right? Now I transmit through the surface, and the electric field on the other side of the surface is smaller because I've got a larger dielectric constant on this side than on that side. So a smaller field, right? The only way that I can make this add up to, plus something add up to this, is if the reflected field is out of phase with the incident field. Okay? So I was deliberate in saying, oh gee, I don't know which way it goes, but I do.
And the sign on the reflection coefficient.
Yeah, it actually turns out, because you asked the question, now I dump core. All right. Does anybody know what dump core means? Okay, that goes back to the olden days of computers, where every night, or initially, and then after a while, every few weeks, and then every few months, the systems managers for large computers would have to go in and dump all of the memory, clear the, oh, actually, you have to do that. You used to have to do that when you got the blue screen of death on Microsoft. What you would do is you turn the computer off, and then you turn it back on again, and if it didn't come up properly, you turn it off again, and then you turn it back on again, off and on, until magically it would work. In that process of going off and on, what Microsoft was doing was clearing the registers and clearing the memory. And so the idea of dumping core, what computer scientists, or rather systems managers used to have to do, would be to sort of store everything elsewhere and dump the core memory. And then that became a common phrase for example, when your mothers would visit campus, and then I would just make like a little bit of a question like, oh, how's George doing? And then your mother will dump core on me and tell me everything that was ever recorded from the beginning of time. I don't think I've met your mother, actually, so you're clear.
For now.
For now, yeah. We have to wait for graduations when that will occur, in your case. Okay, so I've got relationships for B fields, which follow from both that and the continuity equations for the electric field. Okay, so let's take a look at the case now. We just take this as given, and given that, what do we end up with when we look through the relationships between the fields? And so what I know what I'm going in with is a choice of the polarization state, and a choice of the angle, and the optical constants of the material, which again are not constant, they depend upon frequency, but we'll call them constants. What are the conditions that I end up with here, right? So for so-called S polarization, so S is perpendicular to the plane of incidence, and that means that the electric field is always parallel to the surface. For P polarization, when the electric field points this way, I've got a component parallel to the surface and perpendicular to the surface. But S polarization is simpler. All right? Then I have E0 plus E0 double prime minus E0 prime perpendicular to the surface is 0. There's nothing perpendicular to the surface. That's it. Right? Actually, I should have written E0 is 0. That term is meaningless. Let me erase it now. And then I have one other. It says that this one follows from the magnetic condition. E over mu, E naught minus E naught double prime, cos theta incident minus square root of epsilon prime over mu prime, E naught prime, magnitude of the field, cos theta transmitted is equal to 0. I have that condition. Just thinking about what else. Oh, yes. I do want to add something over there as a general relationship that we're going to use, which is that, well, first of all, the index of refraction is the square root of mu epsilon. That I told you last time around. And 2 is that n sine theta incident is equal to n prime sine theta transmitted. Snell's law. As long as I warned you that I was going to put in complex numbers, I'm just going to do this to be nasty. All of those things can be complex. They'll have an I in there.
So a tilde over becomes complex.
A tilde over something says beware.
Yeah. I'd like to read-
Spaniards follow.
Yeah, when you run NDA last time, I
No expects suspension position.
No, that means complex.
Got it.
Why can't mu be complex?
Why not?
For everything that we're going to be doing here, mu is 1.
Can it be 1I?
Because we're not going to work with ferromagnetic materials. So mu is close enough to 1 for everything that, it's like 1 plus 10 to the minus 6. It's 1 as far as we're concerned. So that's why I didn't bother to write it down. So out of this then can come some relationships between the transmitted field and the incident field and the reflected field and the incident field. I needed 2 equations. The other one that I wrote up there can be used. So work this out. E0 prime over E0. Which one am I going to write? Yeah, I'll write this one. In my notes, I've given you a couple of different ways to express this, but once you're done just playing with this, 2 cosine theta transmitted sine theta transmitted, oops, incident, cosine theta incident sine theta transmitted over sine theta incident plus theta transmitted. So that's the ratio of the transmitted field to the incident field. What? All right. And the one that I'm usually interested in is the reflected field to the incident field. So the ratio of the reflected field to the incident field is minus sine theta incident minus theta transmitted over sine theta incident plus theta transmitted. We almost always have the same normalization for these ratios. These things here, these ratios of electric fields, can be complex, meaning that they include phase information, and I'll give you some examples for the phase information. What did that mean?
4 minutes left.
Oh, phase information, all right? And they are called the transmission and reflection Fresnel coefficients. So this would be called T, and this would be called R, but we have to be careful. This is for the S polarization, so it's R sub S.
Does it need to be T sub S?
Yes. Okay, so that's one polarization of light incident upon a surface, which would be this polarization coming into the tabletop surface like so. Field pointing in this direction, perpendicular to the plane of incidence. The plane of incidence, to remind you, being this. How many of you have had optics? Yeah, not enough. You should all take optics. It's great.
Professor Schroeder is boss.
Don't take it. Boss?
You learn all about World War II in optics. All right.
From the German side of things.
It's the only history class we have.
That's S polarization. P polarization. And I should comment that I've actually forgotten the origins of the words S and P, which are German, and Senkrecht and P. But Professor Schroeder could and has told you the origin of these words. These letters. Oh, yes. Okay. Well, that's a good way to do it too. But I'm going to use S and P. All right. In that case, we have a different set of boundary conditions that the same boundary conditions, but a different set are important, right? In fact, more of them are important because the P polarization includes components that are parallel to the surface and perpendicular to the surface. Parallel to the plane of incidence and perpendicular to the plane of incidence. I'm wrong. includes components that are parallel and perpendicular to the surface, that's what I meant to say, always in the plane of incidence.